So we have the Hamiltonian, and the very first thing we did, we defined several properties on Tuesday as being derivatives of the energy. Derivatives, first and second derivatives of the energy of a molecule and the electronic energy. Now we have a Hamiltonian. So the next step is then, before we can take derivatives of the energy, we need expressions for the energies. And what we want to go and do there now is, how to calculate the energy. Is that question. And what we want to do here now, there are two approaches, but the first one we look at, we just used the perturbation theory, which we introduced 2 weeks ago. So we use perturbation theory. It is slightly different, and you'll see that in a minute or two, than the one we had before, because we have this H2 term now. So the general expression which I gave you last week, it was on Tuesday, for the nth order energy term or the nth order wave function correction term, you actually have to modify for this situation here, because the H prime, what I call the H prime operator, and in all the counting of orders always assumed to be first order, now it's first and second order. So you can still start from those equations, but you sort of have to rearrange them a bit. Nevertheless, the first order term, that's not a problem. The first order energy correction was a zeroth order wave function, the first order Hamiltonian, and a zeroth order wave function. That's obviously not changed, because that's just first order. But the second order energy is going to be different. Because now, we had the second order energy, we had a term which looked like this: zeroth order wave function, first order Hamiltonian, and a first order wave function, which together gives second order. But I can also get a second order now by doing that, taking the zeroth order wave function and now take my second order Hamiltonian. So this is the extra term which we get here now. And then if we insert that first order wave function, our expression for the first order wave function, and remember that all the higher order wave functions we get by expanding them in a set of known functions. And the known functions are the complete set of zeroth order wave functions, being the eigenfunctions to this one. Then we get, so we get a sum over all basis functions, which are those zeroth order functions. So if we write it up again, so I get here the second order term, and now a sum over all other zeroth order functions. So it's 0, first order Hamiltonian, and now psi n here, which is any of the other zeroth order functions, and that's n different from 0. And again, H1 psi 0 divided by the energy difference, E0, En of those two zeroth order wave functions. And this is this putting in here, and you can see then, either by looking at the notes from last week, that sort of this, all within my bubble, that is our first order wave function. which we set in as being an expansion in the zeroth order wave functions. And essentially, if I take this out, the rest, no, this is the coefficient of that zeroth order basis function in the sum here, which I think I called C1n or something like that last week, first order coefficient. And that is often called, this thing is called a sum over states expression, because it's a sum over all other zeroth order wave functions. And in our case here, those zeroth order wave functions, they are all the solutions to the unperturbed Hamiltonian. And that means they are actually all the states of our molecule. If we would have the molecule alone in vacuum, these are all the states. Psi 0 being the ground state, because we looked in this course here at ground state properties. You don't have to do that. You could also look at an excited state if you want to, but we look at ground states. So all the n's are the other states, meaning they're all the excited states of the molecule. And of course what applies here now is doing that using perturbation theory, not so much using perturbation theory here, and in particular this expansion in those states n, of course implies that I assume that I have solved the equation for this operator. I've solved the zeroth order equation. Which is not really true. I mean, I can't solve that exactly. That's just our normal Schrödinger equation. And we spent a lot of the last 2 weeks on discussing that we can't solve that. We have to do all kinds of things to do that. So this is sort of a bit of an illusion that you actually really, I mean, we don't know those exact states. So what you have to do then is afterwards to make approximations to this expression. But it's still very, very useful to understand properties, to understand the behavior of properties if we remember that we can, if we would know those states, we could express them like this, the properties.